Hey there guys, today we're going to take a look at what we call dependent and independent events. So a couple definitions before we start. If we talk about compound events, we're just talking about two or more events happening. So we're looking at two sort of actions, regardless of what that means. If these events are considered independent events, what this means is that one of the events does not affect the other. So, for instance, if you roll a die and then you flip a coin, those two things don't interact with each other, so the outcome of the first thing won't make a difference towards the second. On the other hand, if we draw a card and then draw a second card, depending what happened on that first card, it will make a difference for that second card you draw. So those would not be independent. Those are dependent events. Okay, so let's take a look at some simple independent events. So a coin is flipped and turns up heads. What is the probability that the second flip will turn up heads? So the idea here is it doesn't matter that I flipped the coin and it came up as heads. The second one is still going to have the same probability. So the probability is still equal to 1 out of 2. Okay? Now, if I flip that same coin 4 times and it turns up heads each time, what is the probability that on the 5th trial it will turn up tails? And, I mean, again, it doesn't matter what happened. The probability of flipping tails is still 1 out of 2. Okay? So, the other flips don't matter, basically. They don't matter. They don't affect it. They have no impact. Okay, so what is the probability of flipping 5 heads in a row? So now this is where it's going to be different. This is going to make it a difference. Whoops. Okay, so we'll say the probability of 5 heads. 5 heads in a row. Okay. So what we're going to do is we're going to say, well, how many ways can I succeed? So the first one, how can you flip a heads on the first toss? Just one way. And then the second toss, it still has to be the heads, and it has to be the heads, it has to be the heads, it has to be the heads. There's only one way for it to happen. Every single one you flip has to be a heads. Now for possibilities, well, the first flip, there's 2 possibilities, heads or tails. Then the second one, there's 2, 2, 2, and 2. And so we just multiply all of those together, and we get that the probability would be 1 in 32, which is 3.1%. Okay, so there you go. So, what is the probability, let's look at the probability of 2 different independent events. So, a coin is flipped while a die is rolled. What is the probability of flipping heads and rolling a 5 in a single trial? Okay, so what we're going to do here is we're just going to say, well, what's the probability of flipping heads? And that's going to be 1 out of 2. And what's the probability of rolling a 5? And that's going to be 1 in 6. So what we're going to do then is we're just going to say, well then what's the probability of heads? I'm going to zoom in here. And 5. So the key word here is and we've seen this before in the last unit, and it works the same actually. What we're going to do is we're just going to take the 2 probabilities, we're going to multiply them, because both of those things have to happen. Okay, so we get 1 in 12, whoops, 1 in 12, which is 8.3%. Okay, and so this gives us the product rule for independent events, which is that, and this is sort of a key here is it'll say with replacement for them to be independent events. So for instance, if you're drawing a card, you have to put the card back in the deck if you're going to draw a second card, or else it's no longer independent. Okay, but the rule is simple enough. If we have the probability of event A occurring and the probability, whoops, not of A again, and event B occurring, you're simply going to take the probability of event A and multiply it by the probability of event B. So if we want both of the things to happen, we're just going to multiply the probabilities. Okay, so let's move on to the next page. There are two tests for a particular antibody. Test A gives a correct result 95% of the time, and test B is accurate 89% of the time. If a patient given both tests, what is the probability that both tests are correct, that they both give the correct result? So this is just, we want the probability of event A, of test A being correct, and the probability of test B being correct. So we just take those two probabilities and we'll write them as decimals, and we just multiply them. Okay. And so that will just give us 0.8455. In other words, it is 84.6% likely. Okay? So there's an 84.6% chance that both tests will be correct. So what is the probability that test A will give us the correct result, but test B will not give us the correct result? So what we're looking for then is we're looking for the probability of event A occurring and event B not occurring. That was a notation we did earlier. It is also worth noting that the probability of event B not occurring is going to be 1 minus the probability of event B occurring. Okay, and so what that gives us is that the probability of event, because it was an 89% chance that test B would be correct, that means that we'll have a 0.11 or 11% chance that B will not be correct. So the probability that A is correct and B is incorrect is going to just be 0.95 times 0.11. Oops, too many ones. And that works out to be 10.5%. Okay. All right. So, what is the probability that neither test will give the correct result? So this is a case where, obviously, we want this number to be very small in this context. So we'll take a look. So what we're looking for then is we want probability of A to not happen and B to not happen. Okay, so we already talked about B being 0.11. Event A was 95% likely to happen, so that means that A not happening is going to be 0.05. Which, oh, hold on, let me actually write that down, sorry. I'm getting ahead of myself. Okay, so we'll have 1 minus 0.95, and we'll multiply that by that 0.11 that we already found. Okay, so we'll get 0.05 times 0.11, okay, which is going to be 0.0055. So it will be 0.55%. So just over 0.5% likely that both tests will be wrong. So very unlikely. Okay, so let's take a look at this next question. I'm going to throw you a little bit of a curveball, and this is one thing that you have to watch out for on tests, because I do this. It will definitely come up at some point. You're going to read the question. We see that we want to find out the chances that A will not be correct, but B will be correct. The trick here is that I asked for the odds, not the probability. Now, we have to find the probability first. So we'll do that. and then we'll worry about the odds. Don't wait until the very end to find the odds, but always make sure you check your questions to find out, is this an odds question or is this a probability question? So we want A to be wrong, and we want B to be correct. Okay. So we'll just have the 0.05 times the 0.89, which gives us 0.0445. Okay. So what we're going to want to do is we're going to want to write this as a fraction. Okay. Now, some of your calculators will do this for you. I mean, there's lots of ways you can express that as a fraction. I'm going to write it as, well, hold on, let me just write fraction. So I want a fraction, and I'm going to write that as 89 over 2,000 equals, okay, and I want to remember the probability was the chances of success over the chances of success plus the chances of failure. Okay, so from that we can see that, let me zoom in here. So from that we can see that H is equal to 89, and we can see that K is going to be 2,000 minus 89. Okay, in other words, it's going to be 1,911. Okay, if you had done it as 445 over 10,000, you would have gotten different numbers for H and K, and then you would have gotten, when you wrote it as odds, you'd be able to reduce the ratio. But anyway, so this gives us the odds as 89 to 1,911. So remember, this is the number of ways of success over the number of ways of failure. Okay, that's the difference between odds and probability. All right, so let's look at conditional probability. So this is when we look at dependent events. So this is what I talked about with the playing cards, where the first event affects the other event. So we're going to say this is one event. The event depends on another. Okay. So the rule we have is just that if we want the probability of event A and event B to occur, it's going to be the probability of event A times the probability of event B given that A occurs. So let's write out what that means. This is probability of B given that A occurs. Okay, so I'm going to walk you through an example here to make it clear what that means. So it's prom time, and Patrick's friend assures him that if he asks Brenda to prom, there's an 85% chance that she will say yes. There's a 60% chance that Patrick will actually gather the courage to ask Brenda. So we're going to find the odds that they will be at prom together. So to begin with, remember, I am asking for odds here, okay? But remember, always just start with probability. Do probability first. When you read the question, make a note that it is an odds question. Do the probability, and then go back and change it into odds, okay? So, first of all, let's look at what the events are. So our first event is that Patrick actually asks Brenda. So he has to ask Brenda. Okay? And then event B is that Brenda says yes. Okay? it is worth noting here, Brenda can't say yes if Patrick doesn't ask. So Brenda can't say yes if not asked. Okay? And so this is what makes this a dependent problem here. Okay? It depends what happens, whether Patrick actually asks Brenda or not, whether she will say yes. Okay? So let's just go, and this isn't particularly challenging at this point once you figure out what it is we want. So we will have the probability of event A and B, okay, and that's going to be 0.6 times 0.85, okay, which is just going to give us 0.51 or 51%. Okay, so let's just quickly look at the, because of course we just want Brenda to say yes. Like, to succeed in this, we really actually only need Brenda to say yes. The thing is, in this question, oh, hold on, I can't zoom in, there we go. In this question, if I wanted to find the probability that Patrick doesn't say, or doesn't ask Brenda, and Brenda says yes, well, that would be, you'd have a 0.4 chance that Patrick won't ask, I think. Is that what it was? Yeah, 0.4. Okay, so there's 0.4% or 0.4 chance that Patrick won't ask Brenda. But then we have to multiply by the probability that Brenda will say yes, given that she's not asked, which, as we talked about earlier, is just 0. So the answer is 0. So this is where we can sort of disregard this situation, okay? So anyway, the only thing that's left is the odds, because I didn't ask probability. I asked, I'm not sure why I put, it doesn't belong to odds. There we go, okay. So the odds then, well, the number of ways of succeeding, so probability was 51 out of 100. Okay, so which means the odds are going to be 51 to 49. Okay, and that's that. All right, well, let's jump over to the next one. Okay, so we've got Caitlin has examinations coming up. She's got data management. She's got biology class. She estimates the odds in her favor of passing data management are 17 to 3, and her odds against passing biology exam are 3 to 7. We will assume that these are independent events, okay? And we'll get to, in part C, we'll talk about why they are not in real life, but if we assume that they are independent, we want to find out what the probability that Caitlin will pass both exams is. So the first thing I'm going to do is I'm going to say, so we'll make A, we'll make she passes data management, okay, and we'll have B, she passes bio, okay. So we have the odds of these things. We don't really want the odds of these things because we're going to work with probability. So what I'm going to do is I'm going to convert them. I'm going to say the probability of A is going to be, so there were 17 ways, that she could pass data management, and then the total number of outcomes, well, it was 17 to 3, so on the bottom we're going to have the 17 plus the 3, so it's going to give us 17 out of 20. Okay, the probability of her passing biology, so the number of ways you could succeed, and you have to really pay attention on this one because it actually gives you the odds against her passing. So on top we're going to have the 7, not the 3, okay, and then on the bottom we'll have the 3 plus 7, so we've just got 7 out of 10, okay. So the probability that she will pass both data and bio, it's just going to be 0, well, hold on, let's do it. I did it as fractions earlier, so let's just leave it how we're doing it. We'll have 17 over 20 times 7 over 10, which is going to give us 119 out of 200, which equals 59.5%. Okay. And there we go. So what are the odds in favor of Caitlin failing both exams? The odds in favor of her failing both exams. So we want the probability. Again, always start with probability. Don't worry about the odds until the end. So we're going to say probability of A prime and B prime. Okay. So the odds of her, or the probability of her failing data is 3 out of 20. Okay, and then we'll have 3 out of 10 for bio. So we're left with 9 out of 200, which means we have 900 ways of succeeding, which is a failure in this case, but you understand. Okay, so H is 9, and then K is going to be the 200 minus 9. So the odds, which I guess I should write out, is 191. So the odds are going to be 9 to 191. Okay. All right, so what factors can make these two events dependent? And so this just means, like, why is it in real life that one of these things would affect the other? And there's lots of different reasons here. Obviously, if she spends too much time on data, or on one, spends time on one, that means less on the other. She could just get discouraged. Oh, I spelled that wrong. No, and I can't even correct it. There we go. Discouraged. Yeah, well, whatever. And there's lots of other reasons. I mean, yeah, whatever. You get the idea. Lots of different things that could make it, and so I'm sure you can come up with a few others. But the idea is that in real life, these things are not actually independent. And if it's a question of something that's controversial like this, I'll either specify in the class. I will usually specify in the question, but if I don't, feel free to ask for something like that. Okay. All right. So that's it for this time. Until next time, go Sabres.